actually more about the device-independent quantum key distribution. Please, Rotem.
Thank you. It's actually doing, okay. Thanks, Norbert. Yes, so I'm Rotem. I will tell you about device-independent quantum key distribution. I will try to focus on the security proofs and practical challenges. This will be the structure of the talk. I will start with some introduction, explain what device-independent QKD is. Then I will present the standard protocol that is being studied. From there, we'll go to some proof techniques and the challenges and open questions. What do we need to do next in order to have an experiment that implements device-independent QKD? Okay. Good. Okay, so let's start with the introduction. So what is device-independent QKD? Why would we like to consider such a scenario? And how can it be possible? Okay. So I'm starting exactly basically where Norbert started yesterday. So what is QKD? We have two honest parties, Alice and Bob. They have their physical devices, and they would like to produce a shared private random key. So these will be these bit strings here. Okay. They want to have identical keys, and they want these to be private, meaning that no one else knows anything about their key. Okay, so we introduce another party, a dishonest party, Eve. And Eve's goal is to gain as much information as possible on these keys. Okay, so for that, she can do many different things. So whatever Norbert said yesterday, these crazy things, she can try to attack the system. Okay, now we're switching to the device-independent case. So in the device-independent case, we actually give Eve more power. So now Eve also prepares the devices that Alice and Bob are going to use. So Alice and Bob, they don't know what's going on here. Eve tells them that there are some quantum states inside, and the devices are measuring these quantum states in order to produce a key. But in practice, maybe there is a chip inside, and they basically don't know if this chip is useful for something. Okay, so they must treat their devices as these boxes where they have no idea what's going on inside. Still, we want them to be able to create a private key out of these devices. Okay, so this is the challenge. Okay, why would we want to do something as crazy as that? Okay, so device independence basically means that the security of the produced key is independent of the implementation of the device. Okay, so if we manage to prove security, if we manage to prove that they get a secured key without looking inside, then it means that the security is valid for any implementation of the device. Okay, so why? So first of all, we can take the cryptographic point of view. Okay, so here we can say, okay, maybe I bought my device from some foreign country and I don't trust the manufacturer. Okay, and still I want to be able to create a key. Okay, so this is kind of this extreme cryptographic point of view. And another option is maybe for a more realistic point of view, which is important, is that the physical devices are imperfect. Okay, so as Norbert explained yesterday, we have this concept of device and a model of device, and these things we can never make sure that they match. Okay, so there are always some imperfections in the device that we can't fully characterize. Okay, we can do our best to get a model and then apply a security proof which is relevant for that model, but there will always be some imperfections in the device that we can't really control. We can't know in advance what's going to go wrong in an experiment. Okay, and of course there is also, just because it's interesting, okay, so by learning, studying the concept of device-independent cryptography, we actually learn about fundamental aspects of quantum physics. Okay, we're pushing cryptography to the limit, and it also motivates new models, like some intermediate cases, like semi-device independent cryptography. Good. Okay, how can we do such a thing? Okay, so how can we do something useful if we don't know what's going on inside the device? Or if you want to phrase it slightly different way, how can we distinguish these two cases? Okay, so we want to be able to say, okay, there is something quantum which is useful going on inside the device, and it's not really that we have a chip. Okay, so this system, maybe we can get a key out of that, and these chips, probably we don't want to trust the keys that they give us. Okay, so how can we distinguish these two cases? And the idea is to play what's called a non-local game. So the most famous non-local game is the CHSH game. Okay, so maybe you're already familiar with it. And this is how we model the situation. So now instead of these of these two devices, I switch to this kind of figure. So I have here still this device with the two parts. So one part is for Alice, one part is for Bob. Okay, and we don't know what's going on inside, which means that we can't open this device and see and interact with it directly. What we can do is just interact with it in a classical way. What does it mean? So there are buttons here on Alice's side, for example, and she can choose an input, a classical input X. So this will be for the CHSH, let's say 0 or 1. Okay, and according to this value 0, 1, she can push the 0 button or the 1 button. Okay, and then the device will do something and will spit out another number A, which will also be a bit 0, 1. Okay, and similarly for Bob, so Bob can choose his input Y, and the device will do something, and it will give it this output B. Okay, so now we can think of the Alice and Bob's interaction with this box as a game. Okay, so when they start the game, they make sure that these two parts of the device, they do not communicate. So this is like having these two parts far away. So they give the inputs, they choose random inputs, 0 and 1, then the device gives them their outputs, and then they check whether this winning condition holds or not. Okay, so this is just a condition. If this is satisfied, then they say that the device wins the game, and if not, then the device lost. Okay. So this is a non-local game, an example for a non-local game, and it turns out that it has a very special property. Okay, so the best classical strategy, so if there is a ship here inside, achieves up to 75% winning probability. Okay, so a ship can't do better in this game than winning 75% of the times. On the other hand, there exists a quantum strategy that can lead us to win around 85% of the time. Okay, so there is a gap here. This is what we call a quantum advantage. So a quantum device can do better than any classical device. Okay, and this is something that we want to take advantage of in order to do device-independent cryptography. This is what allows us to kind of distinguish these two cases. Okay, let's get slightly more technical to explain this, how we can use this concept for to do something, a cryptographic task. Okay, so let me now look at what we call a correlation space. Okay, so now my box, I have these inputs and the outputs. These are just the numbers, and I can basically model it as a conditional probability distribution. Okay, so this describes the behavior of this box, what happens when I give x0 and y0, for example. Okay, now I can look at the space of correlation, so the space of probability distributions. We can have here the quantum set. So these are all probability distributions that arise from measuring quantum states. Okay, and we can look at the subspace of classical correlations. So this is all the probability distribution that can come out by using classical strategies. Okay, so each box like this is basically a point in this space. Then we can see a non-local game, or Bell inequality is basically something like this line here that separates these two areas. Okay, so if we win below a certain threshold, then it's possible that we're in the classical set, and if we win above a certain threshold, then we know that we are in this quantum regime. Okay, so a classical strategy is a classical that can be written in this form. It's a convex combination of these product distributions. Okay, so this is what's also called the local hidden variable model, for those who are familiar with it. And the important point here is that because we're in device-independent setting, so this device is prepared by Eve. Okay, so she's the one to choose these probabilities. Okay, and if we have a classical strategy, then she can always choose the probabilities here in a way that basically, given the knowledge about this x and lambda, okay, this information here, she gains the information about A. She knows what A is. Okay, and similarly for Bob. So if she knows A and B, then clearly we can't get any key out of A and B. Okay, because she has full information, we can't do any cryptographic task. On the other extreme, if we look at the optimal strategy for the CHSH game, it turns out, so this will be a point here, and it turns out that this is, all of these strategies are basically measuring the maximally entangled state. Okay, so if Alice and Bob now share, if we know that they achieve this optimal winning probability for the CHSH, we know that they basically have this maximally entangled state, which also means that if we now consider Eve, so we purify the system to Eve, actually it means that Eve is in tensor product with Alice and Bob systems. Okay? And from this we can, with some additional information about the measurements here, we know that Eve basically has no knowledge about Alice and Bob's system. Okay, so this is what kind of intuitively what allows us to produce some information which is unknown to Eve. Okay, getting again slightly more technical. So if we want to quantify these statements, so we can choose some measure of uncertainty. Okay, so a certain entropy. So this is the von Neumann entropy, and basically this describes how random Alice's output is, A, from the point of view of Eve. Okay, so E is Eve's quantum system, and X, Y are the inputs for the game that Alice and Bob are choosing. Okay, so this basically tells us how random Alice's output is from Eve's point of view. Okay, and you can see if we have this plot, this was derived by Pironi et al. A decade ago. You can see we have these two extreme cases. So a classical strategy, I told you this gets you up to 75%. So this is really this extreme point here, and we see that we have zero entropy. Okay, meaning Eve can gain full information about Alice's output. And on the other extreme, the optimal CHSH, then we are in this point, and here we have full entropy. Okay, meaning that Alice can produce this bit A, and Eve has no information. Okay, and then you can take basically any point in this correlation space, and if you know the winning probability of this in the CHSH game, okay, so how well it's doing compared to this line here, then you can put it here on this curve and get you know how much entropy you have in Alice's output, okay, as a function of the winning probability. Okay, questions so far? Okay, yeah, thank you. Omega is the winning probability of in the CHSH game of this strategy. Okay, so we will say for the classical strategy, omega will be this 75%, and for the quantum one, it will be this approximately 85. Okay, so omega I'm always using for the winning probability. Thanks for a specific strategy. Okay, perfect. Thank you. Okay. So what is the structure of the protocol that we consider? So let me start by assumption. Then the protocol is basically a combination of two main steps. The first one is generating the raw data, and the second one is some classical post-processing. Okay, so the assumptions are basically similar to what Norbert mentioned yesterday. These are the standard assumptions that we're also using in a device-independent case. So Alice and Bob's physical location are secure. Okay, so Eve is not standing there and watches what they're doing. But there is another important point here is that they can basically restrict the communication between their secure locations whenever they want. Okay, so when we're playing the games, I said that the two devices are not allowed to communicate, so we need to be able to make sure that we can stop the communication between the two locations. We have a trusted random number generator to choose the inputs. We have trusted classical post-processing units. Okay, so this means that they can just, they can perform classical calculations. They have authenticated but public classical channel. So this means that they can talk on the phone. Okay, Eve can listen, so this is a public channel, but it's authenticated, which means that Alice knows that she's talking to Bob and vice versa. Okay, so it's authenticated but public classical channel, and we assume that quantum physics is correct. Okay, another important comment. So I said here that we need to be able to restrict the communication between Alice and Bob's device, but we do allow, in general, communication between Alice and Bob and from Eve to Alice and Bob between the different rounds of the protocol. So you will see in a second that we have rounds of the protocol. And this is important if we want to be able to implement the protocol by distributed entanglement on the fly. Okay, we don't want to send all of the entangled state in the beginning and then just tell them, okay, do not communicate at all, but we want to send entangled pair, then wait, do something, then send another one, and so on. Okay, so we do allow for communication during the protocol. We just need to be able to decide ourselves when we allow it and when we stop it. Okay, good. So far we had this model, we had this tiny little box, and we could play one game, so we can give one input and get one output. But clearly, if we want now a protocol, if we want to generate a key, then this is not enough. We will need to interact with these bigger systems, okay, or bigger boxes, you can think of them, that allow us to play many rounds, many games, or to give a lot of inputs and get a lot of data out. Okay, and this data that we are going to generate with this bigger box, this data will be used both for testing the device to see that the device is doing what we want it to do, and to generate the key. Okay, so some of the data we will get to actually generate several bits of a key. So what do? We take this box, then we randomly choose in each round, okay, for each, you can see for each kind of group here, okay, we randomly choose whether we are going to perform a test or a generation round. If it's a test round, then what Alice and Bob are going to do is to play a non-local game, like the CHSH game, with the device, okay? So they're going to choose random inputs, so let's say the first one is a test round, they're going to choose random inputs here and get the outputs, okay? They get the outputs, they record them, they write them on the side, and we keep them for something that we call parameter estimation in a second. If they choose to perform a generation round, okay, not a test round, then they will give a device some predefined fixed input pair, okay, so they don't need to choose randomly the inputs. So they will just give a fixed input here, and they will get the data. They will keep it, and this will be used as the raw data for producing the key later on. Now, just a quick comment. So this step of generating the data, we can do it in two ways. So the way I explained now, this is what it's called sequential interaction. Okay, so we do it round by round. First, we choose whether it's a test round, the first one. We do it, then we wait to get the outputs, then we do the second one, and so on. This is how we continue. Okay, but we could also consider parallel interaction, and this will mean that we still choose everything randomly, as I explained here, but then we give all of the inputs to this device at once, and we are getting all of the outputs together. Okay, so this is just some distinction between parallel and sequential interaction. I will mostly discuss the sequential interaction. This is the most well-studied scenario. Okay, good. So Alice and Bob interact. They give this, so you can see this is, let's say, an example for a string of inputs, X and Y, and they get the outputs from the device. So this is their data. And now I marked here the test rounds. Okay, so these are the test rounds. This is the inputs that they choose for the test rounds and the outputs that they get. Maybe one crucial part is that, of course, we want the device not to be able to cheat. So we want to make sure that the device, Alice's device in particular, cannot distinguish the cases where we're having a test round from a generation round. Okay, otherwise the device could just, in the test round, behave nicely, and in the generation round just gives us something deterministic. Okay, so the important point here is, if you look, for example, at these two rounds here, so Alice's device here, we get the input 0 in both cases, and she can't know, or Alice's device can't know whether it's now a generation round or a test round. Okay, so this is just maybe something for the intuition, if you want to keep it in mind. Okay, so we got the data, and now we want to do something with it. So now we're moving to the classical post-processing. The first thing that we need to do is parameter estimation. This is the part where we're basically testing the device. We're checking whether the device is sufficiently good for us in order to produce a key. Okay, so what we're going to do, we're going to take the test round, then we are going to check whether the game is won or not in each of these rounds. Okay, so let's say this is I checked, and this is, okay, in these rounds, the game is won. In these ones, it loses. And then parameter estimation is basically this very simple thing, is we're just counting how many times we won the game, and then if it's above a certain threshold, this threshold is a parameter of the protocol. If it's above this threshold, then we're saying, good, continue, the device should be fine, and if not, then we abort the protocol. We're saying, okay, this device is not good enough for us, we don't want to continue with it. Okay, and maybe just one comment. This is, if I play just one game, this is the simplest thing that I can do, but you can imagine more general, more sophisticated things. So we can, for example, consider two different Bell inequalities or different tests, and then we can, look for different thresholds. Maybe we want these supposed to be green things to be above a certain threshold, and the orange ones above another threshold. Okay, so this is just, you can get creative with the thing, and you can choose to have different parameter estimation steps. Okay, so this was the parameter estimation. We choose whether to continue or abort, and then there are two additional steps that I will describe in slightly more detail later. But let me just mention, so we have an error correction step. This is a part where we want to make sure that Alice and Bob share the same data, because we want them to have the same key in the end. Okay, and in this step also there is a point in the protocol where we can say that we want to abort the protocol if it doesn't work. And the final step is what we call a privacy amplification step. The goal there is to make sure that if doesn't have any information about the final key. Okay, so we will get to them later. For now, one thing that I wanted to mention is that in these protocols that we consider, these two steps are implemented using one-way classical communication. Okay, so this means that Alice will basically do something on her side, some classical calculation. She will send this information to Bob, and then Bob will do something, but Bob will not send any information back. Okay, so this is what we call one-way communication for this classical post-processing. Okay, so I'll say a word about that later. Okay, any questions about the protocol? Yes, you can. So, I mean, there are two different ways, but usually let's take the simplest thing. We're just doing it publicly, okay? And we take this information into account in the security proof. Otherwise, you can go for the other option, which is kind of saying we don't do it publicly, they just choose independently, and then we do this sifting stage that we say, okay, maybe these rounds are not relevant. So it will come up in a different point in the analysis. Yes, sorry? Yes. It's public if knows. The important thing is that the device, okay, so first of all, Eve prepares the device, gives it to them. So the device in advance doesn't know in advance which rounds will be test rounds or not. Okay, and then as we go, we choose them, we communicate it publicly. So this is information that will be available for Eve, but only after the fact. Okay, so when she gives them the device, she doesn't know in advance which rounds will be the generation or the test rounds. This is very important, thank you.
I don't think you told us what Bob's box does when input is 2.
In what it's supposed to do, or?
Yeah, what it's supposed to do. Because
in the honest case, you mean?
0, 1, and 2 for Bob, so it's not CSSH game anymore. What does it say?
Yes, so first of all, we're in a device-independent case, right? So the box is doing something, and we don't care what it is, so I cannot enforce the actions of the device for this one. What it's supposed to do is that, so it's not that relevant in general, but so what we're supposed to do is that we're supposed to have in the optimal case, let's say, a maximally entangled state, and then for this the input 2, we will just make sure that they measure in the same basis. The reason that we need this is that then when they measure in the same basis, they get correlated bits, right? And this will just allow us to get better key rates for later. Okay, so you don't have to do it. This is something that you're doing in order to kind of minimize error correction in the end. So it improves the key rate. Okay, so in general, you will ask Bob to perform a specific measurement in the same basis as the measurement that Alice is performing for 0, and it will just improve the key rate. Okay, but I think it's not that. No, you're still looking puzzled. Okay. Okay, so maybe just let me give it another try. So in the test rounds, right, we're just playing the CHSH. In the generation rounds, our goal is to generate a key. For generating a key, we would like Alice and Bob's outputs to be identical. Outputs. Okay, we want the keys to be the same. And for this, if we want to optimize the key rate, it makes sense to ask Bob to perform a different measurement, which is not a measurement that he's using for the CHSH case. Okay, so we just ask him to perform a different measurement that will make the outputs more correlated between Alice and Bob, and therefore we'll lose less information later. But this is just for optimizing the key. Okay, yeah?
You mentioned for the error correction that you want to have a one-way error correction. Is that really important that's one-way, or can we do the again the thing is important thing we apply a key map like Alice as a key map, and that result does not change, but you can use two-way communication. But Alice defines what is that we want to correct to.
I think I will reach that in the end. I think the point is that we don't know of any good two-way communication protocols. So I mean, we first need to find a protocol, and then we see, whether we can do it this way or not. But I think the point of having a two-way is exactly not to do that. Is exactly to make sure that you can maybe use extra information. So if Alice just fixes her key, then I don't know what you will do with the information from Bob. Okay, but let me try to get back to this later. Okay, so this is the protocol. Let's start looking at the proof technique. How do we actually prove security of such protocols? Okay, so I will just start with some brief history. Then we'll discuss quickly the security definition. I will explain what is the main task, what do we try to do when we prove security. Then I will touch the most important things of how to achieve this main task with a technique which is called the entropy accumulation in this context of device-independent QKD, and a few words about the classical post-processing. Good. Okay, so history, again, split here to the parallel and sequential protocols, sequential interactions. So most of the work is just with sequential protocols. The first two works that basically gave the main ideas that started this entire field, these famous works by Eckert and Myers and Yao. So they just gave kind of the main concept. And then we got a proof of concept from Barrett, Hardy, and Kent. Okay, so this proof of concept, this means, I mean, they just got one bit, and in a case where there isn't any noise, but this was just to say, okay, it is possible to take take a bell violation and get a key out of it to get a secure bit. Okay, then later, Pironio et al., they analyzed not the most general case, not the most general quantum adversary, but something that we call an IID and asymptotic case. I will explain it later. What it is, but this is kind of a restrictive adversary, quantum adversary. And for this case, they, and the protocol that I just described, with the CHSH, they got tight key rates and noise tolerance. Okay, so this was a very important result. Several years later, we got extended this basically to general security, so a general quantum adversary without these assumptions, with various techniques. But here then we didn't, once that we got the general security, we didn't get to match these parameters anymore. Okay, so noise tolerance, for example, was much lower than the noise tolerance that we have here. And then recently, and there was this, these new works that allow us to get the general security, so the most general quantum adversary, but match these tie rates and noise tolerance, okay, which is important if you actually want to implement the protocols. And this technique is based on this entropy accumulation theorem, which was developed by Dupuy, Fuzzy, and Renner. Okay, so we have these two works that give us slightly different quantitative results here. Okay, so this is the main tool which is used to get a general security with the tight rates and noise tolerance. Independently of that, there is another technique which is based on something which is called probability estimators. So we will hear about this later this week, and I will say another word later. So there, this idea of probability estimators started with considering, again, a classical adversary, so not the most general thing, and then recently extended to the general security, general quantum adversary. In these works, it's not about a device-independent QKD, it's about device-independent randomness, but you can directly extend it to the QKD case, and then you get to match the same rates, I think. Okay, so this is the sequential case. In the parallel case, so this is the case where I just give the device all of the inputs at once and I get all of the outputs. So this model was introduced by Jen, Miller, and Chi a couple of years ago, and the first security proof was given, and then later Vidic simplified this proof. In both of these cases, the parameters that we are getting are, this is just kind of a proof of concept, I will say. It's far, far from what we have in the sequential protocol, so I think it's more a theoretical thing at this stage, but it's interesting to consider it, see whether it's possible to get something which is similar to the sequential case. Okay. So we're doing cryptography. The most important thing is what is the security definition, okay? We don't want just to prove something, we want to make sure that we are proving the right thing. So let me start by kind of intuitive understanding of what it is, a security definition for the QKD case. Okay, so if the device is sufficiently good, okay, if we don't abort, what we want is to actually get a key, okay, a secure key. So what does it mean? It means that we want Alice and Bob to have the same keys, okay, so we want identical keys, and we want it to be unknown to Eve. Okay, it should be private. Okay, the other option is that the device is just not good. Okay, either it's malicious or it's too noisy or whatever. What we want to do in that case is just to be able to detect it. We want to say, okay, abort. This is not good. I don't want to create a key. And another requirement is we want to be able to say that actually we can implement a protocol. Okay, so there exists an implementation of the device, implementation of the protocol that will not abort. Okay, that will actually we can actually get a key. Otherwise, it's not very useful. These things, we can give them names. So identical keys, this we call it correctness. The combination of unknown to Eve and aborting, if the device is not good, this is what we call secrecy. Okay, so this is, Norbert mentioned this yesterday. Okay, if we abort, then clearly the key is secure because there isn't a key. The combination of these two things, this is what I call soundness. And the final requirement here that there exists a device, We call it completeness, or I also call it noise tolerance. Okay, so this is just in words. There is a mathematical way of formulating it. So again, these appeared in Norbert's slide. I will not get really into the details, but you can see we have the correctness, meaning that they are with high probability they're the same. This is the secrecy requirement. It also appeared yesterday. And we have the completeness statement, which means that there exists a device that will not result in aborting with too high probability. Okay, so the important thing is that the soundness, this is kind of proving that for any device, any malicious device, we get the right thing, and the completeness just says there exists a device that can implement the task. Okay, and I think the most important comment here is that, here I gave you the intuition, and then I put this security definition, but this doesn't come from the sky, okay? So it's not like I had the intuition and I said, this is the right way of formulating it. Okay, these security definitions, they come from, there is a way of deriving them, and this you can go back to tutorials by Renato Renner from last year and Christopher Portman tutorial from 2 years ago about composable security. So there is an entire framework that allows us to make sure that we are getting to the correct security definition. And if we prove security for this definition, then we're good to go. Still, this security definition is actually, it's good, it's composable when you're doing normal QKD. It turns out that for device-independent QKD, this security definition is not composable. Okay, it's not fully composable. We use it because it's the best thing that we have right now. It's the best thing that we understand, so it's almost composable. So again, this appears also in Christopher's tutorial, and I can also answer questions later. But here I'm just saying it because most of the papers you will see, we prove device-independent QKD or other device-independent tasks. We prove composable security, and it's not the exact statement. Okay. So we are using this security definition. This is the best we can have. We understand what it can or cannot do, but it's not fully composable. Okay. We have security definition. We want to prove security. What do we do? Okay, so what's the hard part? We said we're trying to prove security. For this, we need to prove two things. We need the completeness and the soundness. Completeness is usually the easier part. So let's look at the soundness. Soundness, for that we need to prove correctness, so we have the same keys, and secrecy. Again, correctness is usually the easier part, so let's go to secrecy. Secrecy basically depends on the privacy amplification step that I will mention later in more detail, but this one, the privacy amplification, is basically just applying a function that we call an extractor, and if the extractor works, then we get the secrecy. Okay, so we're going back here. Now what we need to kind of show is that this extractor works. I will explain what it means later. And it turns out that this extractor works if we have a sufficiently amount of mean entropy or smooth mean entropy in the data, in the raw data on which we apply the extractor. Okay, so this quantity, this lower bound on the smooth mean entropy, this is what tightly determines, if you go in this direction, this is what tightly determines the maximal length of a secure key that you can produce from your device-independent QKD protocol. Okay, we will get back to this idea. Maybe it will get more concrete later, but for now, my point is this is what we need to do. Our main task is just to find a lower bound on the smooth mean entropy of the raw data. Okay, this is what we are going to discuss. So there are different techniques on how to do it. The two most recent and tight approaches, the one based on this entropy accumulation, and the other one that I mentioned about probability estimators. I think morally, from my understanding, they're more or less the same, but I would say that maybe the important thing is that this one is more analytically oriented, and this is more numerically oriented. So it depends on your preference. If you are more of an analytical person, then maybe look at this first, and if you prefer the numerics, then maybe that would be a good starting point. Okay, and I will focus on this technique, but Jan Bouw will give a talk on Thursday about this approach and an experiment that uses this. Okay, so stay tuned. Okay, so I will talk about entropy accumulation in the context of device-independent QKD, and I will not give the entire thing. I will mention just the most important thing, the best practices of if you want to start using this. I will mention the most important thing, but not all the details. In my PhD thesis, I wrote much more, so more than appears in all of the papers. And these chapters on the thesis, these are supposed to really, take you by the hand. So if you want to use this, you get a bit of, I think, some intuition and explanation from what I'm going to explain now, but then you can go to the thesis and really, understand really all the details and do it one step one step after the other. So if you want to use this approach, I would recommend looking at it. And then maybe one comment, I explain it here in the talk in the context of device-independent QKD, but it can be relevant for other things as well, for other protocols, for other QKD models or for other cryptographic protocols, okay, and not just randomness. So maybe even if you don't care about device-independent QKD, you can stay with me, and it can be useful also for other things. Okay, let me. Okay, sorry. Okay, so I think to explain this approach, the easiest way is to start with what we call the IID assumption. Okay, that I mentioned before that there is such a thing, but I didn't explain what it is, so let me do it now. So IID assumption, IID stands for independent, identically distributed assumption. So we're considering this scenario, so it's not the most general device, not the most general adversary, a device that the adversary can prepare, but you can imagine a device, IID device like this thing here. So we have just many independent, identical copies of these smaller boxes that I had in the beginning. Okay, so each box is kind of just an independent copy. And now when we want to use this box, then we basically play the games or perform the rounds of the protocol, each one separately. Okay, so let's say we have a test round with this box, then we go to the next box, we're doing another test round. So because we have these separated boxes, and under this assumption, what happens is that the actions of this box, what happens in this round, is completely independent of the previous one. Okay, so this is what I mean, it's independent. Okay, and identical is doing also exactly the same thing. Okay, so this is in the IID assumption, this is the situation that we consider. So we play the game many times independently and identically. And then what we're doing is we're using the data that was generated in order to estimate the winning probability in a single game. Okay, so it's an IID setting. We can use, let's say, Chernoff bound. We just get all the data, and from this we see, okay, if we have, we won above a certain threshold, then this is a good estimation of the winning probability of just one box like this. And if we get back to this curve that we had before, once we know the winning probability of, a single box, then we know that for a single input, this is the amount of entropy that we get. Okay. Now there is a great tool which is called the quantum asymptotic equipartition property, okay, by Michael and al. What this gives us is basically it tells us that the total amount of smooth mean entropy. Okay, so this is just the smooth mean entropy. The vectors I'm using the bold letters to indicate that I'm taking now all of these A's. Okay, so it's not just one. It's not just A1, for example. It's A1 to AN. Okay, so the smooth mean entropy of Alice's outcomes, given all of the side information, the inputs and ifs system and whatever else, is lower bounded by this thing here. So we have here two terms. So the first term, the first order term, this is linear in n. It's just the number of games, the number of boxes that we have here, times the von Neumann entropy from a single round. So, okay, so we have this number of boxes, and here I told you we estimate the winning probability, and we get the von Neumann entropy of a single round. So this gives us here this first term here. And then there is a second order term which behaves like square root n. Okay, so if you care about the finite statistics, the finite key rate, you will need also this one. Yeah, Jill?
Does this depend if it's sequential parallel?
Sorry?
Does this depend if it's sequential?
Okay. Good. So Jill is asking whether this bound depends on sequential parallel. So this bound is only for the IID case. Okay, so in the IID case, we actually don't care if it's sequential or parallel. Yeah, but that's important. Okay, the crucial part is that this is a great tool. It gives us directly, you see, once we have this object, so once we understand the behavior of the entropy as a function of the winning probability, then with the quantum asymptotic equipartition property, we're basically done. Okay, but this tool is relevant only for the IID case. Good. So now we're moving away. Now we're moving away from this IID. We want to consider this more general setting. Now we're looking at a sequential setting. Okay, so this, what I'm going to say now, is only relevant for the sequential case. So we are moving from the IID to the sequential. We can no longer use the AEP. the asymptotic repetition property. And this is where the entropy accumulation theorem, the EAT, enters. Okay, so it will basically replace the AEP for this sequential case. Okay, so our goal is basically to replace the AEP. Our goal is to find a bound like this on the smooth mean entropy. So I have the same quantity here. I care about all of Alice's output and the side information, and I want to find a lower bound with these two terms. The first order term has this; it's linear in n and has this some t. Okay, we will talk about it. And there is another second order term that behaves like square root n. Okay, so this is what we want to do. The question is basically, what is this t? Okay, this is what we are trying to find out now. So in the case of the AEP, we said this t is the entropy that we get from a single box. And this made sense because there was a single box. But when we go to the sequential case here, we have this huge thing, and I mean, there isn't any object which we can think of as just this one system. So we need to understand what t is here. Okay, and I hope it will become clear. Okay. So the entropy accumulation is a tool that can be used in some sense to reduce this case of analyzing the sequential setting to the IID setting. Now it's important that it's in some sense, okay? It's not just a black box reduction. So what do I mean by this? You can't just prove security for the IID case and then say, I'm done. You know, I can use the entropy accumulation and then I have general security. This is not correct. Okay, so it's not enough just to analyze the IID. You just need to make sure that certain conditions, okay, you need to construct some objects, make sure that certain conditions hold, and only then you can say, okay, now I take what I know from the IID case, and I take the conditions that I learned, and I'm using the entropy accumulation. Okay, so it's not a black box reduction. And this is why it's important for me to explain what are these conditions, what are the first thing that you must do before you can actually apply this entropy accumulation theorem in this context. Okay, so these are the things that I will focus on right now, and then you can go and do it yourself when you analyze your own protocol. Okay, so we said entropy accumulation is relevant for sequential protocols, sequential processes. So we need to define the process. This is something that we call EAT channels. So I'll explain what this is. Then there are certain conditions that the EAT channels must satisfy. The most important ones are certain Markov chain conditions that make sure that entropy accumulates. So I want to explain those. And finally, there is an object that we need to construct, which is called the mean trade-off function. And this mean trade-off function is the thing that will allow us to find this t that was missing in the previous slide. Okay, so let's get started. The first thing that we need to do is to find a way to model our sequential process. And by this process that I'm talking about, this is a combination of both the protocol of what Alice and Bob are doing in the protocol and the thing that the device is doing. Okay, so also the actions of the device. We're in a device-independent setting, so we don't know what the device is doing. Okay, we don't need to assume a specific action, but we just know that it's doing something. Okay, so there is some quantum operation, some quantum measurements on quantum state that describe these actions of the device. Okay, so this is the only thing that we need to do to know just that there is something. Okay. So this is maybe a way of modeling a sequential process, so if we can have this picture in mind. So we start with some initial state. Okay, this is the thing that we don't know what it is. Okay, so Eve chooses this state. It's an unknown initial state, and I split it here to two parts. Okay, so one part is the part that it's Eve's system, it's Eve's register. So this part we just think of it. Okay, this is this register here, and we don't touch it, right? Eve prepared this. She keeps the system for herself, and that's it. We don't do anything with it. And the second part of this state, these are the registers that belong to Alice and Bob. They're the ones that are inside the device. And this is the part of the state that we are going to process during the protocol. Okay, so this is Eve. Okay, so now there is a process, okay, this sequential process, the protocol and the device, that takes this state and basically it's like applying a sequence of maps, of quantum maps. Okay, so we have, in the beginning we have a state, then a map, the first map is acting on this state, it will output something, it will output another thing, I will make a distinction, and then maybe there is some post-measurement state and some memory that the device is keeping, we don't know exactly what it's doing, and this will be transferred to the next map and so on. So this will be the sequence, the sequential process that happens here, and then in the end, what we get is this final state here. Okay. So how do we model these maps? So these are what we will call the EAT channels. So these maps, there is the input state, there is the output state that will go to the next step in the process, and there are these two outputs here. One of them we call the outputs, and one of them we call the side information. Okay, so we will have freedom in choosing which outputs of the channels we choose them we call them the outputs, and which outputs are the side information. This is up to us to decide. So in the device independent case, I just call these outputs, I choose the channel such that these outputs are Alice and Bob's outputs. Okay, so we play the game, or we have the generation round, so we give the inputs. The box gives us values for A and B, okay, 0, 1, and this will be this value that we assign here. You look puzzled. No, N, you're good. No, these are just the two random variables. So it's the value of A and the value of B. Thanks. Okay, so this is in the device independent case. This is I just choose this O1 to be these two random variables. Okay, so I keep these two values. Okay, the side information, what I call here the SI, this will be the inputs. Okay, so I keep here, I'm saying my channel outputs here AI, BI, and the channel also outputs Alice and Bob's inputs XI and YI. Okay, again, just these two values, and if there is more side information, then whatever it enters here. Yeah. Sorry?
The channel outputs the inputs.
Yes. Okay, so we need the channel basically. This is a description of the entire process. Okay, now the entire process, what happens? Alice and Bob run the protocol, they choose the inputs, right? This is a part of the information that you have. So this is also, you can think of this channel describing Alice and Bob choosing the inputs, okay? Then the device is doing something, the device is producing the outputs, and then you're outputting the outputs. Okay, so you're recording both of the inputs and the outputs, right? This is information that you are going to use when you analyze the protocol. Okay? No, yeah. Yes, these channels, they describe the combination of both the protocols, so both of it's what Alice and Bob are doing, and the actions of the device. So this is really the entire process. Here we start with the initial state. It doesn't include the inputs. Okay, and then as part of the action in each step, Alice and Bob choose their inputs. They trust the process in which they choose the input. I'm just saying this, I need this information, so I call it this. It's one of the outputs of the channel, and this is what I decide to call the side information that this step in the process kind of outputs. Okay, so it's also side information you can think of it because this is something that is revealed to Eve, right? So this is kind of information that in this step of the protocol is information that is released the outside. Okay, so really depending on the protocol, you will need to analyze it, and you need to choose how you define the process. But this process is really it's not just the device. It's really everything that's going on, the entire way that you're starting from the initial quantum state to your final quantum state. Okay, then there is another thing. So I have this information, the inputs and the outputs, right? In my protocol, I'm going to do some parameter estimation. I'm going to check which rounds of the test rounds are won and which are not. So I add here another random variable, C, okay, which is basically just whether we win or lose the game in this round. Okay, so here I have, you see, I have in each one of them, I have the outputs and the inputs, so I can check whether I won the game or not. So this is also some kind of, in a sense, an output of the channel. Okay, so I'm checking whether I won or not, and I keep this information here. It's another random variable. Okay, so this is the process, and our goal will be what the entropy accumulation will give us. Our goal will be to get a lower bound to understand what is the smooth mean entropy of the outputs given the side information produced by the channels and the quantum side information that the adversary gave. Okay, so in our case, this will be finding the smooth mean entropy of the outputs A and B given the inputs and Eve's information. Okay, these are supposed to be bold vectors, so this is all of the outputs together. Okay, so we model the process. Now the each channels, they should fulfill certain conditions. Okay, so it's not any way that you model it will count as an each channel for the theorem. The most important one is a Markov chain condition, this thing here. So this is basically the condition that makes sure that entropy actually accumulates in the process. Okay, so I'll explain it a little bit. So we have here our process again. The Markov chain condition that we care about is this thing here. So let's try to process it. It basically means that for each round, okay, so for each I, the side information, which is produced in the ith round, is independent of all of the previous outputs. Okay, so all the outputs that were produced before, given the side information that we had before. Okay, so it basically means that, you know, if in one round you're not kind of destroying the outputs, the entropy of the outputs that were produced before. Okay, maybe before you kind of understand this, you can just look at the device-independent case. Here it's trivial. So if I look at the way I chose these random variables before, basically this boils down to saying the x and the y, the inputs of round I, okay, are completely independent of the previous outputs, all the outputs that I got in the previous rounds, giving the inputs of the previous rounds and the adversary. And this is trivially right, because I choose in each round, Alice and Bob, they choose the inputs independently of everything else, so in particular, independently of the outputs. Okay, so for this choice, the Markov chain conditions, they hold. Okay, so again, just in the sense of the kind of intuition, so this basically means that you need to have this, because this means that future steps do not reduce the entropy that was already accumulated. So if we're kind of thinking of a process where we're slowly accumulating entropy, if in the end the final side information just leaks everything, then we don't have any entropy left. Okay, so maybe just important thing to note is that the way I choose the channels and model my sequential process, it matters, okay? Because it might be that for a certain choice, these Markov chain conditions will not hold, and then you cannot apply the entropy accumulation, okay? Or maybe there is another way of doing something which is less trivial, and then you can actually make it work. Okay, so it might require a bit of creativity, but if you're doing kind of QKD or device-independent QKD, then the things that we already have in these works might, you know, do just well. Okay. The last object is the mean trade-off function. Okay, so we start with this question, what is this T here? And then in the case of the asymptotic equipartition property, in the IID case, this was the von Neumann entropy. So now, basically, the mean trade-off function, this is the object that is going to tell us what the value of T here should be, such that we get the right value, the right bound. Okay, so it's a bit maybe hard to understand right away. So the mean trade-off function, this is the worst case von Neumann entropy in a single round restricted to the correct average winning probability. Okay, so maybe the equation is easier. Now we have a situation where we're looking kind of at one part of the process. Okay, we have some initial state here that will enter to this channel. There is the side information, and my channel is going to give me the outputs and the inputs as before, and we are going to check whether we win the game or not. So f-min, this is a function that you need to construct. Okay, you need to define a function, and it's a function that should satisfy this condition. So here what we have is the von Neumann entropy of the outputs. This is evaluated on the state in the end of this channel. Okay, on the output, so you win, let's say you play the game, right, with this state sigma that enters, so this is what happens, this is what the map is doing. Then you want to know, okay, on the output, what is the entropy here? And you take the worst case state, the worst case sigma, but not just, you don't take all possible sigmas, but only states, initial states, that lead you to winning this game with probability which is greater than this omega. Okay, so this is a function of omega, and basically here you have infimum over states which give you this correct omega. Okay, so this is a function that you need to construct. If we take this curve that we had before we used in the IID case, or just in intuition, so this blue curve that we had from before, this basically gives you the mean trade-off function. Okay, so the mean, because we had it for any Bell violation, we knew what is the entropy. Okay, then we can choose f-min to be basically this function here. And you can now see, let's say that we have, in our protocol, we have a certain threshold. We say, okay, we abort if we win less than this amount of games, so this will be my threshold. So in all of this regime, I abort the protocol, I don't care. And this is the regime where I continue with the protocol. I won more than this threshold. And then basically, if I take the mean trade-off function, and I take the value of this entropy at this point of the threshold, this is what T should be. Okay, so if you take this t, then you get the right bound here. Okay. So then what we get from the it in the end of the day, so again, I didn't write the entire theorem, but what we get in the end of the day is this. We get a total smooth mean entropy. It's evaluated on a final state in the end of the protocol, condition not aborting. Then we have these two terms, the first and second order term, as we wanted. The first one is linear in n, the second one is square root n. And this t, this is the value which is given by the mean trade-off function for the observed statistics, okay, for the point in which you abort the protocol. Okay. Maybe some urgent questions? No, okay. Okay, so a bit quickly about the classical post-processing. Okay, so we have the entropy. This was the hard part. Now we need to do some error correction. Okay, I apologize. I'll do it really quickly. So we have the row keys that we got from the generation rounds. You can see they're not necessarily the same. So we need to apply another protocol, error correction protocol, that will make sure that Bob corrects outputs his key to Alice's key. This is done with one-way communication, meaning Alice is doing something, then she sends this information over the public authenticated channel to Bob, which means because this is public, then some information is leaked during this process to Eve. Okay, so if we had this initial entropy that we got from the entropy accumulation, we now lose some of it just because we do this additional error correction step. Okay, so instead of the mean entropy that we had before, now we need to reduce some amount of entropy. Okay, and this implies also that even though, even sometimes in some cases we can have entropy, so we can, for example, produce randomness, but this is still not enough in order to get a positive key rate. Okay, so there is a regime of parameters where we can get entropy but not key rate because we need to reduce this entropy. Okay, so this is the error correction and the privacy amplification. This is basically the step that after now Alice and Bob have the same raw data, now they need to make sure that Eve doesn't know anything about the final key. So this is the privacy amplification step. It removes the remaining correlation with the adversary at the cost of getting a shorter key. Okay, so we kind of squeeze things together. And this is done using what is called the quantum-proof randomness extractor. This is a function, a classical function that takes us from A to the final key. The important thing about this function is that if we have enough entropy, then we get this kind of trace distance, which means that we are indeed getting to something which is close to the ideal key, and Eve doesn't know anything about that. Okay, and here for more information, there was another tutorial in QCrypt 2013 by Arnon-Friedman. So you can learn more about quantum-proof extractors. Okay, so if you remember this slide, okay, we said, okay, in order to prove security, the main thing we need to get is a lower bound on the smooth mean entropy. So now, let's say that we have, okay, so I show you how we get this bound. Okay, if we have this bound, then we can say, okay, this extractor that I briefly showed you a slide ago, this extractor works. Okay, so the condition for the extractor to work is this a bound on the smooth mean entropy, and this condition, this is directly related to this condition that we had for the secrecy. Okay, so this is now you can see why, in order to prove security, the main thing was to get this lower bound on the smooth mean entropy. Okay, good. So this is what we know how to do. We know how to prove security of this structure of the protocols. What do we want to do next? Okay, so if you follow this security proof, this approach, you look in the papers, then you get these plots. You see the entropy rate, how much randomness we can basically certify from a given Bell violation. Okay, so if we see in the protocol a specific average Bell violation, and this is the amount of entropy you can certify. Current experiments, they're somewhere here. Okay, so if you want to certify, there are already experiments that certify device-independent randomness. Okay, they have a very low violation. Okay, so it's really next to the classical thing, but sufficiently many rounds such that we can still certify entropy. Okay. Unfortunately, if you now go to the QKD case, so I said there is a gap, we need to do error correction, so it's not that any amount of entropy directly gives us a positive key rate. So if you look at the QKD key rate, again from the paper, The only important thing to understand here is that there is a fundamental threshold here for these models that we consider, which what we can see here is that if we are below winning probability of 0.8, then the key rate is 0. Okay, which means that the current experiments, okay, we're good, we're getting entropy, but we don't get the key rate. Okay, so basically, even though we have this theory, even though we have this tight analysis of the protocol, we're still far from the experimental abilities. Okay, so we have this problem here. This one is tight for this protocol, but it's not good enough. Okay, so the main question, the main challenge, how can we bridge the gap? If we really want to have an experiment for device-independent QKD, what can we do? So, I mean, the easiest solution for me is like, go ahead, invest a lot of money and give me better experiments, but then I'll be done. So let me try to say, okay, what can we do on the theory side? What can we try to improve? Okay, so the device-independent QKD protocol that we analyze and the analysis, the security proof, they are tight. Okay, so there you can't really improve that. Okay, what you want to do is you want to look for different protocols. Okay, if you find different protocols, maybe they will do better, and then we will be closer to the experimental abilities. Okay, so the first thing, so going back to Norbut's question, the first thing that we can try to do is to change the classical post-processing steps. So the optimality of the protocol, it's optimal only with respect to protocols which use one-way classical communication in the post-processing, so only one-way error correction and privacy amplification. It might be that if we go to two-way classical post-processing, we can get better key rates. Okay, that's completely possible. The main challenge is that we just don't know of any two-way protocols. Okay, so there right now people are starting to look at it, but we're basically looking for two-way, it's called advanced distillation protocols, and we need to prove their security. So we need to find a protocol, and then we need to show that we can actually get security from that. Okay, so this is, it's hard, it's not easy, but that can be one way to go. The other thing that we can do is optimality. Again, it was optimality for the CHSH game. Okay, so maybe you want to change the game. You don't want to do the CHSH. So the question is whether there is a better non-local game that can allow it to certify more entropy. Here, the main challenge is the following. So if you switch the Bell inequality, the only thing that you need to change in the security analysis is the mean trade-off function. Okay, so you can just change them. If you find a good mean trade-off function, you get the tight result for this new Bell inequality. The problem is if you want to get a tight bound, you need the mean trade-off function it's defined with the von Neumann entropy. Okay, and it's hard to get a tight bound for the von Neumann entropy. Okay, we don't know how to do it in general. We know how to do it for the mean entropy with numerical analysis. This is with the SDP hierarchies, but for the von Neumann entropy, we don't know how to do it. So the main question here is, okay, first of all, maybe you can get an analytical bound, but if not, is it possible to come up with a numerical technique that I can just, give a Bell inequality and it will give me a bound on the von Neumann entropy? Okay, and this we will hear some first attempts in the next session. Okay, another thing which I think can be useful is the analysis of no-click events. Okay, so we know that in the experiments, okay, or as far as I know, in the experiments, the reason that we are here is that most of the times we don't even get entangled states. Okay, so the detectors, they don't even click. And we cannot just drop these events, okay, because this opens what's called a loophole. Okay, so what we need to do instead when we're analyzing these no-click events, we just assign a random value. This is basically like a classical strategy, and this is why the Bell violation is so low. Okay, so the question is whether we can somehow take the no-click events in a more refined way in a security proof. Okay, so for example, you can try to modify the protocol such that Alice and Bob will announce the no-click events, but clearly then you can't just use the same security proof. You need to change also the way that we analyze the protocol. For example, you need to take into account this additional information which is leaked during the protocol when you devise the mean trade-off function. So again, I don't think it's easy, but I think, it's possible to, it's an interesting direction. It may be possible, and I think no one is looking at it right now. Okay, and maybe the sad truth is just, there aren't any better protocols. This is what we have now. It's kind of more or less the best that we can do. And you shouldn't waste your time on finding new protocols. So still, how can we know if this is the case? So if you want to see if it's worth your effort to look for other protocols, what you need to do is actually to look for upper bounds on device-independent QKD key rates. Okay, so what does it mean? We basically need to kind of say, okay, let me model all possible device-independent QKD protocols and see whether I can say, okay, all of these protocols, fundamentally, they cannot give me more than this amount of key rate. Okay, so for the CHSH protocol, we have a tight lower bound, so we know what we can get. And if you can get an argument that works for all device-independent QKD protocols or family of them and say, okay, here you can't do much better, then we know what is the gap. We know how much we can hope to improve. Okay, so this will give us some kind of, it will tell us whether we should even be optimistic or not. It's a hard thing to do because the argument should hold for any device-independent QKD protocol. And again, first step in this direction will be in the next talk. Okay, and the other option is to say, okay, we can't do anything really good with device-independent QKD. Let's go for semi-device-independent QKD. There are many different models that one can consider. So first of all, it's an interesting discussion to say, okay, which one is the most interesting one. And then after we've, for each of the models, it's important to do this to tight and non-asymptotic analysis of the key rate. So I think in most works right now, the analysis we maybe say, okay, in this semi-device independent approach, we know that the detector efficiency, the threshold is better than in device independent case, but no one really is doing an analysis, or as far as I know, an analysis which actually tells us, okay, in this regime of parameters, which is relevant for experiment, this semi-device independent protocol is doing significantly better than a device independent setting. Okay, so this is if we want to just say something concrete about where semi-device independent QKD is doing better than the full device independent, then we need to perform this tight and non-asymptotic analysis. Okay, yeah, we heard about one model of the semi-device independent case yesterday, and there is another one on Thursday. Good. With this I end. Thank you.
Thank you very much for the excellent tutorial, Rotem. Thank you very much.
Thank you.
Questions? I see one question here.
Thank you. Yeah, totally awesome. Thank you. I have two questions. The most pressing is that you said that these proofs of security are not fully composable. How badly are they not composable? And in particular, can at least these keys be used as a one-time pad to send a message afterwards? So is it can you do anything with these keys that are fully composable?
Yes. You can do almost everything. So yes, first of all, you can do a one-time pad or whatever.
Good.
Yes, you can use it in any classical thing you want afterwards. Okay. The only thing which is problematic is really this tiny detail that in a device-independent setting, what happens? You need to think what happens if you actually compose the protocol with itself. And not just the protocol with itself, but you're actually reusing the same device, the same physical device. Okay, so what happens is that if you're using the same physical device, the device can keep the memory from the first run and then kind of use this information in the second round. As long as you can kind of think of what you're doing in a situation where this memory from a first protocol to a second protocol is erased, then you're fine. So if you used your device, okay, you got the entire key. So what I'm saying now, it's not like the IID assumption. It's not like, run the entire protocol, you have just one device with memory, then you're done, throw it to the garbage, and then do whatever you want. So if you're doing something classical, of course, you're not using the device. And if you want to do another QKD or I don't know what, quantum authentication, whatever, just do it with a different device, then you're good to go. Okay, but if you really want this extreme situation where you're reusing the same device and you're kind of allowing this memory, then you're not good. So it's composable, but in general, if you say fully composable, then you mean it's composable in any possible way. And there is this detail that if you compose it with itself, with memory, then things break down.
Excellent, thank you. My other question is that as assumptions in one of the initial slides, one assumption, not surprisingly, is that quantum theory is correct. But you also had an assumption in parentheses and complete. What did you mean by complete, and why is it important?
Okay, so complete basically means that there isn't something which is stronger than that. So the adversary is also limited by quantum physics. So correctness means I can, everything I do is fine. So the completeness means that there isn't something else. The reason that it was kind of in a side remark is that we only require completeness in this regime this regime of physics that we care about. So this kind of implementing the protocol, and there is a result showing that if you assume correctness for these kind of Bell inequalities, you also get completeness. So you also get that even if the adversary was stronger, she has no more information than the quantum one. So this is it's a cool result that shows this. So this is why it was so basically you only need to assume correctness in this regime, and then you also get the completeness. So you're fine.
Okay, yeah, a very nice talk. I also have 2 questions. So the first question is sort of a follow on the memory problem, right? In your Markov chain condition, you essentially assume there's no memory in the device. I mean, so each one is independent. What do you assume?
No, that's exactly the point. So we want to allow for memory in the device. This is why when we do this sequential process, where let me maybe. Okay, so that's exactly the point. This is why we don't. The point is not to assume the IID. So there is memory in the device. Okay, and this memory. These are the way that we model here. The sequence of channels. So we have this first state. It goes here, and then this map also outputs something that this is the memory of the device. It's everything which the device wants to transfer to the next step. So there is a memory, and then the Markov chain condition basically tells you, okay. What you need to know is just these conditions about the outputs, right? So you're not the Markov chain condition. So you have this process. The Markov chain condition, it says something about these registers here and the adversary. So it doesn't refer to this R. Okay, and if you have a sequential process, so you do have memory. Okay, and if you can make sure that for these outputs. This Markov chain condition holds, then it means that entropy accumulates even though there is memory.
Wait, but does it mean that the output, say, Sn, cannot depend on the earlier input or something? I'm trying to understand what these conditions mean.
In this case?
Yeah.
Yes. So it means So what I'm saying, it's not. I don't call it an assumption because this is something that you need to prove. Okay. If you prove it, then you're good to go. So here, what it means is that yes, let's take the last round. The inputs of the last rounds are independent of the previous outputs. Okay, but the inputs in the last round, these are just the things that Alice and Bob choose, the classical randomness they choose by themselves, right? So they are independent. This is how you construct your protocol. So, so first of all, I'm saying, it's not an assumption, it's something that we prove, and it's just, for this choice, it's trivial to prove it.
Okay, the second question is for the mean trade-off function. Do you know how to construct it for a general protocol, not non-DI protocol? I mean, like decoy scale or whatever.
I don't know. There is one walk, right, in the non-device independent where you can get numerical bounds on the entropy, fundamental entropy, right? So you're asking the normal QKD, yes. So, yeah, Norbert has something I cannot say more details. I think the main challenge, or in the semi-device independent case, also the talk that we saw yesterday, this was also kind of a direction for the semi-device independent case to get this mean trade-off function. Understand that it's not tight, but this is a way to go. And the device independent, we don't have a general way, and there will be in the next session starting point.
Okay. You said there might be a case where we can make use of no-click case in a better way for the better implementation of DIQKD.
Sorry, again?
No-click case. You said there might be a case we can make use of this no-click case.
No clicks, yes.
Yeah. And right now, how do we treat this no-click case in this each channel?
Yeah. So the no-click events, basically what you're doing with them, it doesn't appear in the security proof, but you don't have this option. So when we analyze it on the theoretical model, we just have these 0, 1 outputs, right? So there isn't a special sign for no-click. which means when I get the data and I want to see what is the key rate, I already get just 0, 1. Then the question is, okay, you run the experiment, your data is not 0, 1, it's 0, 1, no click, and how do you give it to me? So what is this step that you're doing? So now if you don't want to open a loophole, the thing that you need, it depends on your experiment. What you need to do is, like, for example, without heralding, what you need to do is just assign a number. Tell me, if you see this special sign for no click, you need to tell me this is 0, this is 1, because I don't know what to do with no click. Okay, and when you do this, basically you're not opening a loophole, but effectively what you're doing is that you're reducing the bell violation.
Yes, so thank you for the nice talk. So I also want to ask 2 questions. So the first question is, like, in the test round and the key generation round, so for the input and output, so they will be the same for these 2 rounds. And the second question is, if this is yes, then what's the error correction for the raw key A and B? Because, like, the winning probability will be almost around 0.8, so means this error will be very high. If this error correction based on this, like, CHSH game, then how can you do the error correction for the A and B? Yeah.
Okay. Okay. So the inputs. Maybe also. So this is related to what Norbert asked in the beginning. Okay. Let's take this one. Okay. So the inputs are not the same for the test rounds and the generation rounds. So they are the same for Alice, but not for Bob. So you can see here, the marked ones are the test rounds. Here I'm getting just the 1 and the 0s for the inputs for Bob. For the generation rounds, we have a fixed input, which is 0 for Alice and 2 for Bob. Okay, so Alice doesn't have an additional one. Alice only has this 0 and 1, but Bob has this special input too. Okay, and the reason that we have this is exactly because we want to reduce the amount of error, like leakage due to error correction. So what happens is that for the CHSH is exactly what you're saying. If they just measure in the 0, 1 the same measurement, then they will not be fully correlated. So this 2 in the honest implementation, this input 2, this basically says, okay, Bob should measure in the same basis as Alice is measuring for the 0 input. Okay, and then in the perfect case, they're fully correlated, so you don't need to do any error correction. And of course, if there is noise, then they're less correlated, but it will be still better than because you have this special input, then this is what will make sure that you don't have to do a lot of error correction. So it optimizes the key rate.
Okay, there's one last question. Is it 1 or 2?
So actually on this slide, so Alice and Bob's inputs are both random, determined by random number generators, right? So Alice would have 0 or 1, and then Bob would have 0, 1, or 2. So I notice on this slide that Bob only seems to have a 2 when Alice has picked a 0. Is that only when it's possible to pick a 2, or?
Okay, so it depends really how you define the protocol. So in this case, I took the simplest thing, that basically they are first of all together. Let's say Alice chooses whether this is a test round, generation round, and then she tells Bob. Okay, so if they choose together, basically with classical communication, if this is a test round or generation round, then every time that it's generation round and Bob picks a 2, then Alice will always pick a 0. Okay, so we will always have just this 0, 2. You can consider a different protocol where you're saying, they choose independently, they don't communicate it, and then sometimes you will have 1 and 2, and then they will do a sifting stage where they will remove these things. Okay, so I think it doesn't. You can do the security analysis in both cases, and I think this way you get actually better key rate.
Okay, so in this case it would be whoever is responsible for choosing whether it's test or generation would select a 2, and then the other value doesn't matter? And they'd go from there? No,
so let's say Alice chooses whether it's a test round or generation. If she chose a generation round, then she's going to tell Bob about this. Okay, and now for the generation round, they just use this fixed input. Alice is 0 and Bob is 2.
Okay, that makes sense. Thanks.
Okay, there's a very, very, very last question.
So, well, it will be 2 really quick questions. Okay. First of all, how reasonable do you think it is to assume that Alice chooses the round type and she tells Bob, but the devices are not aware of the round type? Because if they were, it would be tricky. Because at the beginning of the talk, you said that your adversary might be the one providing you the boxes. So if it is actually your adversary, he might design, and you emphasized that, okay, it's your adversary, but he will only know the round type afterwards, after she or he gave the boxes, okay? But if it's actually malicious, it could design the boxes in such a way that when it's a round type, a test round, it performs a bell measurements. But if it's a key round, it gives you bits from a list of pre-existing key. So how reasonable it is to assume that it might be malicious, your provider, but the boxes are not aware of the round type?
Okay, so this is, I mean, you don't need to assume this. This is just, it just holds. So what happens here, you can also see. So okay, the device was prepared in advance when the adversary doesn't know yet which rounds are going to be test rounds and which rounds are going to be generation rounds, right? So now we think of Alice's device, and Alice's device, you see there is no 2. There is only 0 and 1. So in a generation round, basically if you look at this, it is here, this is a generation round, right? And this is a test round. But Alice's device got 0 here, and it got 0 here, okay? So from Alice's device, you know, it doesn't know whether Bob is giving 1 or 2. So Alice's device doesn't know whether this is a generation or a test round. So there is no way for it to behave differently in a test round and a generation round. Okay, the device cannot distinguish these two cases.
Okay.
So it's important that Alice doesn't have a special, you know, that there isn't a 2 also for Alice.
Yes, but in the original description, there's this round type bit, T, which is known to the parties. And in some sense, you're assuming it's not known to the boxes.
The box is just a box. Okay, it's a computer.
The box, yeah.
Yeah. So I mean, you don't know it in advance, and then the only thing that the box is getting is Alice is pushing a button, 0 and 1. Okay, so there isn't, you know, assuming the box is not kind of. There are only 2 buttons, and this is the interaction.
Okay, I think we probably should go for the computer.
You can come to ask me later. Okay.